All right, I think we'll get started. So welcome to the last week of MATSE 556. As a reminder, I just put up a Dropbox for your final paper, so you could submit it there, and a Dropbox for a link to your final presentation. So no one volunteered to do their presentation live on Zoom. I don't blame you, but you can record your presentation, either voice over PowerPoint slides, or you can use Zoom to record yourself giving a presentation if you want to do it in front of a whiteboard or something like that. However you want to record some kind of video / multimedia presentation, you can put it up on YouTube or Box or OneDrive or something and just submit the link so I can view it. And remember to open the sharing permissions on your link. So sometimes it doesn't like me to sign in, or if you share it with me, it gets weird. So just make it a public link. No one will find it, and then you can take it down after you get a grade for the course. So that should be all the assignments for the course, but I will remind you that you need to complete every assignment. So if you're missing like homework number 3 or homework number 5, turn them in late. That's no problem. I will grade them and take a look at them. And I will also look through the Canvas assignments to make sure that everyone has assigned grades. And I will remind you if something's missing. But it's really important that you get everything in so I can give you a complete grade for the semester. Also, if something's going to be late, or if you have problems at the end of the semester, because I know things happen, just let me know. We have some leeway with deferred grades, so you can have some extra time, but it's much better for you and me if we get everything done by Friday of finals week. Finally, if anyone has any more topics that they want to cover, I put some more slides in the box folder so you can download those and take a look. We're probably not going to get to all of the slides in the course, and so there will be some material that we don't cover, but if you're interested in talking about something specific, or if you have questions, I'm still available by Zoom this week and finals week, so I'd be happy to do office hours or chat, or just have an individual conversation about anything additive that's needed. Okay, any questions from class, any questions or things you want to talk about before we get started today? All right. I will also remind you to please fill out your SRTEs. I think you have a link for that. But SRTEs are really important because they let me know what's good about the class, what's bad about the class, and especially SRTEs help the next people taking the class. So if you didn't like a topic, or you don't want to talk so much about bioprinting and really want to talk more about automotive, or if you want more polymer physics and less polymer chemistry, or vice versa, the SRTE comments really help to improve the course and help the people coming behind you. So SRTEs are good to give me feedback on how the course went, but they're really helpful for the next students coming. So I don't see SRTEs until midway through January or something like that, well after grades are submitted. So you can be as honest with your feedback as you can be. But please, SRTEs are a great way for me to refine the course year after year and help the program evolve at Penn State. So if you would spend just a couple minutes on your SRTEs, I'd really appreciate it, and your other instructors this semester would appreciate it as well. Okay, any questions on that? All right, so we're on the aerospace lecture, and we're going to talk about aerospace and maybe squeeze in automotive in the last 2 lectures for the semester. And then next week is finals week, so you have time to work on your paper and presentation that's due Friday of finals week, and also concentrate on your other final exams. So we just have 2 more lectures to go, and we're almost home. So we refer back to this table and think about advantages over traditional manufacturing for additive manufacturing. And a lot of these things relate to the aerospace industry. So whether we're doing prototyping, whether we're doing component manufacturing, reducing aircraft weight. We'll talk a lot about that today because that is a major driver of additive manufacturing in aerospace, new engine components, flight certified hardware, and then satellite components where weight is a really big savings. And often for satellite components, you're only making one of them or two of them. So additive is a real natural fit for space applications. And additive has gone a long way for industrialization in the general aerospace industry, including commercial and defense applications. And I think Kyle put up a link in the chat last time about aerospace certification for AM parts. We won't talk too much about certification, but it's a very special part of the aerospace manufacturing industry. How do you certify the materials? How do you certify the component? You know, when you make a part for an airplane, you don't always get to test that part to failure because that part is going to go on an airplane, and you don't produce that many airplanes. And so how do you get certification, statistical reliability, reliability of the manufacturing process and the materials? And so if you're interested in the details of certification, I can connect you with some of those resources, and I'll try and find that link that was put up in the chat last time. But that's an important thing to think about. And if you work in the aerospace industry, you'll hear a lot about certification. So global aerospace industry is relatively big, approaching $1 trillion. And so it's a market we're thinking about because if you can capture a certain percentage of $1 trillion, it's still a big number. And we talked about this table last time. And so A&D is aerospace and defense. And aerospace includes space and satellites. And so there's lots of interesting current applications that people are looking at additive for, and lots of potential applications where people are developing new materials, new additive technologies, new approaches to producing these components. And so additive is a manufacturing technique that's really there to stay in aerospace. Just like biomedical, we've seen a conceptual change from how they made hearing aids or how they made dentures in the past to how they're making hearing aids or dentures today with additive. And that same revolution is happening in aerospace. Now, as consumers, we always don't get to see what those changes are. Of course, a lot of the special parts about airplanes and satellites are hidden from view. But when we go back to flying on airplanes here in the next year or 6 months, hopefully, most every airplane that you fly on commercially is going to have an additively manufactured part on it. So it's a big part of the industry, and there are lots of opportunities for additive in aerospace and defense, and lots of opportunities for polymers and composites in the aerospace industry. So if you look at the bill of materials for something like the Boeing 787, which is the Dreamliner, a significant amount of the airplane, upwards of 80%, is carbon fiber composites, high performance composites, and code word for composites is polymer plus filler, or carbon fiber plus polymer. And so the aerospace industry has been using composites for a long time. And so additive manufacture of those types of materials will be really important going forward. Now there's titanium, there's high performance alloys used in aerospace. And so metal will still be a part of the aerospace industry for a long time. It's hard to make jet engines out of anything else. But polymers and composites are a key material in aerospace, and eventually we'll see that trickle down to automotive. So the first carbon fiber composites were used on airplanes in the 1970s, and now we're seeing carbon fiber composite technology trickle into automotive as lightweighting becomes more important. So again, what we've learned in this class about high performance polymers, composites, and additive manufacturing will have a lot of importance in these fields going forward. And so there's important facets to the aerospace industry to remember when applying additive. And so this is from this Deloitte report, and we'll look at the link here in the next slide. But these are some of the key drivers in the aerospace industry for additive manufacturing. So lower part cost, and decreasing part cost really comes from simplifying the tooling and simplifying the manufacturing of the part. So if you're only going to make 100 airplanes, you have to make the tooling for all those parts. And if you can do additive manufacturing, you don't have to make as many dies or as many casting facilities, etc., in order to manufacture those parts. And so part costs can come down drastically because you're only making so many parts for aerospace, even for commercial aviation. Scrap is important. And so if you're using really expensive materials like carbon fiber and titanium, those are hard to recycle. If you recycle scrap, that has to be a certified process as well. So there's issues with recycling raw materials in the aerospace industry. And so if you can cut down on the scrap rate, that will also decrease costs because you're using premium materials in this sector. Time to market is important. And so setting up manufacturing takes a long time, but additive manufacturing can speed that time to market. Weight is, of course, the big one, because over the lifetime of the airplane, you pay for every pound that the airplane weighs in jet fuel. And so lowering operating costs or increasing the efficiency of vehicles, one of the easiest ways to do that is to make them lighter. And we're seeing that in automobiles as well. The automobile industry has really started to adopt lightweighting strategies, especially for electric vehicles, because you can only hold so much energy on an electric vehicle. And so the easiest way to extend the range of EVs is to make them lighter. And then this issue of the buy to fly ratio, you really don't want to buy a bunch of parts that aren't in the air. And so you only make money on airplanes when they're flying, not when they're sitting on the ground. So you really want to buy a part, put it on an airplane, and do something with it. You don't want to have a warehouse full of spare parts. So this is laid out in this Deloitte report right here. So you can look up this report called 3D Opportunity, Additive Manufacturing Paths to Performance, Innovation, and Growth. That's fine. That's some buzzwords there. But thinking about how additive influences things like supply chain and product changes is interesting. And Deloitte has sort of published this 4-quadrant diagram where if you don't have any supply chain change and no product change, you're sort of in stasis. And so you're just using AM to do the things that we know AM can do. You're doing rapid prototyping and design. You have low rate production. You're just doing routine stuff with additive manufacturing. However, as you get into high product changes, you can think about new products. And so how do you make new products with existing supply chains? So how do you do additive to do new things? Or if you're going to remake the entire industry, both changing the supply chain and changing your products, you have new business models. You can have growth and innovation. There's really interesting facets of AM with mass customization. Supply chain is disrupted, or there's new ways to do supply chain. You could do manufacturing at point of use. And so thinking about the different aspects of what changes are occurring in the industry and what's happening with the products in that industry is a really interesting way to think about how additive manufacturing can contribute to aerospace, to automotive, to consumer goods, to medical and dental. And so this sort of 4-quadrant diagram from Deloitte gives us a map for how we might think about placing additive in specific industries. Is there any questions so far on aerospace or key drivers or unique facets to AM? Okay, I see a question in the chat from Paula. Yes, final project is due the 18th by 5 p.m. So that's Friday of finals week at 5 p.m. That's both paper and presentation, and you can submit it on Canvas so I can see the submission and I'll grade it and get your grades in. They like to have grades in by Monday after finals week. And we're going into the holidays, so I'd like to get grades done as well. And so again, if you have problems meeting the deadline, just give me a heads up on that. I'll encourage you to get it in ASAP because we don't want to let these things drift off. But the 18th, I think, let me check my calendar. The 18th is Friday of finals week, and so please shoot for that. And again, if life intervenes in the meantime, just give me a heads up and we can work it out. Okay, any questions or comments so far? Kyle, if you're listening and you can repaste that link on aerospace certification, I saw it last lecture, but I didn't grab it. I'd have to go back into the chat and find it. If you can paste that link, that'd be great.
Yeah, I'll go. I'll find it. I got it saved here. Yeah, it was just something I found interesting. Something I used. I came from aerospace, so and the key in that document was kind of a request from the FAA, and they helped author it. So
great.
definitely
Yeah,
a good tool.
Great. I'll put it up on Canvas for people to check out because when we started the lecture, qualification and certification is how things are done in aerospace. And so anyone who works in that business needs to be aware of it. Great.
Yeah,
Thank you.
absolutely. Mm-hmm.
So there's a lot of cool case studies out there on aerospace, and this is from Prodways, that's an AM manufacturer. And so what they're doing is they're doing lost wax casting of turbine blades. So they're not AMing the turbine blades themselves because those are made out of metal. Thanks for that link, Kyle. Everyone can check that out. So Prodways is not AMing the turbine blades themselves, but they're AMing the form or the wax model that's used to do this lost wax casting. And so you can check out this case study on their webpage, but we'll walk through it here. And so what they're doing in essence is using AM to make the tool. So they can do more complex shapes. And so reducing weight, increasing efficiency, that's very important. They have two solutions that we'll look at here. So they call this DLP printer their moving light technology. So we'll talk about that in a second. But they use a specific resin for this lost wax method. And if you don't know what lost wax metal casting is, we'll talk about it in a second. But basically, this is a resin that's meant to disappear when they fire this mold in an oven. So they burn away all the resin to create a cavity, and then they pour molten metal in the cavity. So this is a resin specifically designed to go away. We've talked a lot about mechanical properties of polymers. We've talked about composites and how strong they are or what they're used for. But this is a unique design of this DLP resin that's meant to burn out efficiently. And if you've ever taken a metal casting lab, people have used styrofoam. They use wax shapes to do this sort of thing. And so we'll walk through both the printing technology and this lost wax process. But this is, again, not AMing the product that's going out the door, but using AM as a way to develop a tool to do the manufacturing you want. So this slide here with this YouTube video talks about this unique DLP process. And what's important in this process is that they have high resolution that's tiled, or the DLP is done in very small sections in order to get the resolution needed. And we didn't talk too much about microstereolithography or different ways to do DLP stereolithography where you're moving the image around the bath, but this is sort of a general method in order to get high resolution and large area printing using SLA or DLP. And so let me see if YouTube is feeling good about this video here, and we'll take a look at it. All right, here we go.
Prodways aims to open up new opportunities for innovation and production by offering the most efficient additive manufacturing solutions and technologies on the market today. With our exclusive patented moving light technology, Prodways provides a unique solution, combining high precision and industrial production, enabling you to bring value to your market. Prodways moving light technology is an additive manufacturing technology using a vat of liquid resin polymerized by UV light to produce parts. At the heart of this technology is a moving DLP that projects an image made up of 2 million pixels, which sweeps across the platform to polymerize the resin in the areas required by the 3D CAD file of the part. After a single layer is polymerized, the build platform is lowered and a thin layer of new resin covers the surface, and the process is repeated layer upon layer until the part is complete. Prodways moving light technology stands out for its unequaled resolution at 40 microns per pixel for crisp details and superior surface finish on every part of the build platform, and high throughput, up to 10 times faster than market standards. Prodways provides a large range of innovative hybrid and ceramic materials for prototypes, functional parts, and for direct production. Our objective? Provide innovative solutions at every stage of your industrial process, whatever your field of application.
All right, so that's really interesting, and they started with an aerospace fan shroud, and then they transitioned to dental models and other things like that. But it's just showing the types of markets that these additive manufacturing companies are going after. And you saw a lot of familiar products in there and a lot of familiar examples that we've already talked about. So this idea of using custom resins up, if my let me exit out of PowerPoint here and see if it comes back. There we go. Well, it'll come up in a sec. But now that we have different ways to AM parts, whether it's vat polymerization or fused deposition modeling or another AM process, now you can see how to integrate these different types of materials into whatever sort of process you're interested in. So resins that are designed for dentures, or resins that are designed for lost wax casting, or elastomers. And so what we've learned about in this class in terms of formulating new materials or adapting materials to AM processes, you can see now where these companies are getting ideas for how to build materials to address different applications in different industries. And the same industries keep coming up over and over because that's where the easy entry is into the marketplace. Expensive dental appliances, high value aerospace parts, machine tooling, things like that. All right, let's see what the issue is here. Hold on one sec. See if I can just get PowerPoint back. All right, the internet must be feeling a little slow today. But anyway, what we see is that the AM market has identified some of these places where they can enter easily. And so when you look at Prodways or Stratasys or Carbon or Envision Tech, they're all going after some of the same applications with their own innovations in printers and own innovations in materials. And so there's a real competition now between who has the best printing technology, who has the easiest workflow, who's got the best materials, and that's all an interesting evolution in the additive manufacturing business. Oh, what's going on here? All right, bear with me for a second. It's the end of the semester, and so the communication between Box and my PowerPoint is just not doing well. Okay, that might be the end of the videos that we can handle. All right, one more time. Bring up the lecture on my computer here, and I'll share it from my other screen. All right, let me stop sharing here. This might not ever work out. Let me share my screen from Okay, can you all see that?
Yes.
Okay, apologies. It's just one of those days. So I can't write on this set of PowerPoint slides, unfortunately, because it's on my computer. But let me make my way through here, and we'll see if we can get the other PowerPoint sorted out. All right, so we just saw this video. You can check out some others from Prodways, but this idea of making larger scale components with lost wax casting and designing both the printing process and the material to enable something like this. And so this now is a simple demonstration of lost wax casting, but if you've never seen it before, you can check out the Wikipedia if you want to, or Encyclopedia Britannica has a really interesting historical lost wax process. But this is an old way to make metal parts. So if you've ever seen a metal foundry where they do casting, this is one of the methods that they can use in order to get this done. And so here is a wax model, in this case an apple. for what you might want, and you embed that model in a ceramic core or a ceramic cast, and then you burn out the wax, and you have various sprues, they're called, to put the metal in. So when you pour the metal in, the wax evaporates, or you burn the wax out first so you have an empty cavity and you can just pour metal in. And so using additive manufacturing technology, and on the next slide I have, here's metal being poured in to the top of the ceramic core, and you get some final metal shape from that. But using additive technology, now you can have the additive manufacturing resolution and additive manufacturing complexity in the wax part that then you can translate to the cast metal part. So before these wax models were CNC machined, or they were done by hand, or you had to find a way to manufacture the starting model with the resolution, dimensions, complexity that you wanted in your final casting part. But with additive manufacturing, now you can just print these things. And if you're a additive manufacturing hobbyist and have a printer at home, there's a lot of online guides for lost PLA casting. And so one of my former students had an aluminum forge in his backyard because his dad's a mechanical engineer. And so you can melt aluminum at relatively low temperature, and you can make a model out of PLA with your MakerBot or whatever printer you want, and do a very similar process where you embed the PLA in plaster of Paris, fire your mold, burn out all the PLA, and then do investment casting of aluminum using this process. So this has been industrially deployed in addition to direct printing. And so whether you're casting large parts, as we saw in the Prodways example, or direct printing of titanium parts, the aerospace industry has employed both printing tooling and printing the part directly. So this is a news announcement from 2017 on AMing titanium parts to put on Boeing 787 aircraft. And so they talk about this is going to cut their cost down by $2 or $3 million per airplane. And so that's a big deal. And they're expecting approval from the FAA, which has already happened because this article was in 2017. But this is how the aerospace industry is doing business now. And this is starting to proliferate. So if we look at the Ultimaker webpage, where 3D printing is used in aerospace, so they have a lot of case studies and interesting ideas there. Whether it's validating designs and doing some fit testing, or printing in plastic before you try and make everything in titanium. Real life models. If you've ever been in an aerospace company, you know there's lots of models of airplanes and bench or desktop demonstrations and other things as a course of doing business in aerospace. And so they use AM to do a lot of those now. Complex geometries, especially complex geometries of custom parts or of only a couple hundred parts. That's an important part of AM. So there's only so many airplanes made, and there's only so many satellites made. And so being able to do complex parts in one piece is an important part of AM for aerospace. And again, lightness is also important. And we saw an example of topology optimization and how the unique shapes that you can arrive at through topology optimization, additive manufacturing really enables making those shapes where they couldn't be made or machined in the past. So this is all the high level stuff of aerospace. And it turns out that there's a lot of pedestrian stuff in aerospace that we don't necessarily think about. But this is one demonstration here from this news article. And this component that Andreas here is holding is the leg of a seat. So when you go and sit down um, in your 737 or 787, whatever it is, of course, this is right where you put your carry-on bag. And so it turns out that a lot of the furniture in airplanes is expensive and it needs to be light. And so by using AM to redesign seat frames, you can see in the close-up of this, so this is this unique gridded shape. That's interesting. And if you look closely, all of these grids are designed specifically for the stresses of this seat frame. So depending on the loading of the seat frame, depending on your average size person, or thinking about the average size person on an airplane, how do you design a custom grid or a custom lattice in order to deal with those stresses, but make it as light as possible? And so this is possible in the aerospace industry, especially because lightness is so important, especially over the lifetime of the airplane. So you can pay a little bit more for this custom solution, and that will pay off over the lifetime of the airplane. So this is really interesting, and this is using additive in a place where you're like, it's just a seat in an airplane. It's not that interesting, but it can be really important, especially when you start to look at the economics of what this weight savings does. So these are two different Airbus airplanes, the A321 and the A380, which is a ginormous airplane with 615 people in it. And so depending on the weight savings per seat, so you can see that you're saving a little bit less than a kilogram, or about 2 pounds per seat, but the annual fuel savings per aircraft can be tremendous. And the lifetime fleet savings, when you have 100 of these airplanes over 20 years, is a really big number. So this sort of payoff time or cost savings over the lifetime of the object pays for unique manufacturing processes, pays for custom parts, pays for some really interesting things that you can do in aerospace, because you say, well, saving 200 kilograms off an A321 is not really that interesting. That thing probably weighs 50,000 kilograms or something like that, or 100,000 kilograms. I'm not sure how much an airplane weighs, but it's only a fraction of a percent, but it really pays off in terms of fuel savings because of the lightness factor of airplanes. So you can pay for new manufacturing, you can pay for new materials, and you can pay for new designs. Any questions or comments on that? I lost my chat here because I'm sharing from my other computer, but is any points for discussion? All right. So if you're interested in aerospace, or you're interested in advanced materials and AM processes, this is certainly one place to look. And so we've talked a lot about AM of relatively small parts. So even going back here, we've talked about DLP of dentures, or DLP of dental aligners, or DLP of hearing aids, SLA of hearing aids. Those are all small parts. But in order to make the larger parts for aerospace or turbine engines, or even in order to make this seat frame, this is made out of metal, but of course you could think about the corresponding polymer or composite seat frame, you need to have larger format additive manufacturing. And the only one that we've talked about significantly is big area additive manufacturing, where they were doing the locomotor Strati and other larger demonstration articles. But there's a lot of innovation now in using DLP or SLA, or using, in this case, material extrusion AM with fine resolution. So these are all small scale. Let me see if I have a better picture right here. Well, this is a material extrusion AM head that's integrated with now 5 of these multi-head 3D printing robots. So this is basically like a multi-head maker bot where they can get large format prints at high resolution. So when we looked at the big area additive manufacturing, they can make large format prints, but it's at relatively low resolution because of the large printing orifice that they're using. And we saw that in terms of the road size, in terms of the resolution of the object that they were making. And so finding a way to go to high resolution, in this case with material extrusion additive manufacturing, they can integrate all these different print heads together and now print larger parts at high resolution. And this is useful for aerospace because you need to make relatively large components for aerospace because airplanes in general are pretty big. So we won't watch this video because of trying to get the PowerPoint and the video working together today, but I encourage you to check this out. And so people are constantly innovating in this idea of large format additive manufacturing using a lot of the principles that we've discussed throughout this class. So you can take a look at that. So we talked a little bit about seat chairs. And so this is another place where aerospace is really, or additive manufacturing is really useful in aerospace when they're doing now FDM. So this is material extrusion additive manufacturing of Altem 9085, which is an aerospace grade Altem with temperature resistance, chemical resistance, UV, environmental resistance, and also flame retardants that we'll talk about in a second. There's a lot of requirements for aerospace grade materials. And so being able to do FDM for rapid manufacture, in this case of demonstration parts for fit, form, and function, or mock-ups, or production of 1 or 2 or 3 demonstration copies before they go to tooling and injection molding. Now all of these yellowish parts in this airplane cockpit are all Altem. And so Javelin, who makes interiors of aircraft, they're using Stratasys FDM for extrusion of Altem parts that then they can deploy in their custom cockpits for aerospace or for general aviation airplanes. So this is interesting. You don't have to have a custom process or a fancy printer. This is an area where even doing a high value material like Altem, they can get demonstration parts quickly for aerospace interiors. And of course, if we're going to make satellites, and this is one interesting case study, and you can check this out on 3D Hubs. They have a section on aerospace. You can see this case study for production of satellite parts where they go from this sort of garden variety titanium frame. They can do the finite element analysis for all the mechanics they need. They can do the topology optimization, and they come up with this lightweight titanium frame on the right-hand side, where now you can save weight, you can have the same strength. And again, this is has that form of topology optimization where the reinforcement is just where it needs to be, rather than thinking about how do you fabricate this from titanium stock and machine it and everything else. So this can be printed in titanium. And finally, all airplanes are really built like Ferraris. They're all hand assembled. So there's a lot of hand assembled work that needs to be done. And rather than robotic assembly that's all calibrated and ready, like we see a lot of robotic assembly of cars nowadays, you need a lot of jigs and fixtures to guide the hand assembly of airplanes. And so this is just one case study, again, from 3D Hubs of printing jigs and fixtures. And this is not necessarily for aerospace, but this is placing badges on a vehicle. So when you buy a BMW, the model badge is in the exact same place on every single car. When you buy a Mazda or a Honda, the badge is on the same place of every car, and that's not put there by a robot. That's put there by a person. But aligning all those badges is really difficult without some sort of tooling to sit on the same place on all the different cars and allow you to place the badge in the exact same place. And so this might be a pretty routine use of jigs and fixtures, but it's really important and it contributes to the look of the article. So next time you're in a parking lot, or next time you're on an airplane, look at how many labels there are. Look how many things are stuck somewhere. Look how many sort of badges there are for different sorts of things. They're all over the place. And so you need a guide for how to put those on by hand, because someone just doesn't necessarily slap those things on wherever they feel like it. And so there's some really interesting technology for making jigs and fixtures and how to make these user-friendly and ergonomic, because it's someone's responsibility to put all the badges on the 318 eyes. And so they're making hundreds of these things a day. And so you need a way to ergonomically place on all those badges. And I have a nice video about this on in the automotive section. And if we get to it, we'll check that out when we get there. I'll point it out. So same thing if you're going to assemble computer parts, or let's see. So this is some sort of injection molded component right here that this person's holding. And so this is going to be assembled, but in order to hold the part, well, you put the motors in, or put the electronics in, or put the other components in. What they're pointing out here in this picture are the white jigs that are holding the part in a stationary position for assembly. So this component was injection molded, so it's complicated. It was injection molded. That's very interesting. But in order for this person to do the rest of the assembly of the component, whether this is a computer shell or a motor shell or something, I'm not sure, just having these white pillars in the right place is important in the assembly process. And we see that for drilling components as well. So if you want to drill a hole in exactly the right spot in your component, just like you have a drill guide for surgery or dentistry, there are also drill guides for assembly of these jigs and fixtures or assembly of certain parts. And this is important again in aerospace because there's a lot of hand assembly done on an assembly line for an airplane. They generally don't have the robotics manufacturing that the automotive industry is using, just because their number of units per time is a lot less. You make a lot less airplanes per time than you do cars. And so this hand assembly and ergonomic assembly and fail-safe assembly, trained assembly is really important because it's people involved in these processes. And so you want jigs and fixtures to make it ergonomic, easy, and to make the assembly fail-safe. This is just another example right here from Stratasys. And so they're using polymer as a drill guide for, it looks like these braking components. So all of this goes to show that people are still putting together a lot of these industrial assemblies by hand, whether it's automotive or whether it's airplanes. And so this is using additive in the manufacture of whatever components we're interested in, or the assembly of whatever components we're interested in, rather than having to additive all these different things. I mean, even additiving something like this is possible, but if you're making enough of them and you can stand up an injection molding, you'll choose the most economical process for manufacturing this component, but it still needs to be integrated with whatever system it's going to be part of. And so there's a lot of things in airplanes, and there's a lot of components in the interior of airplanes. And so we've talked about turbines, and we'll talk about aircraft wings in a second, but there's a lot of ducting, vents, there's a lot of baffles, there's cable management, there's electrical housing, there's light covers, there's trim, signs, door latches, seat armrests. I mean, all these components in airplanes need to be manufactured in some way. And so additive manufacturing is really a game changer in this industry where you're manufacturing just a few very unique components. And so aircraft manufacturers have taken real advantage of this. And don't forget about the interior of airplanes as well as the functional parts that we point to. So this is just examples of all the different technologies. So whether you're doing fused deposition modeling or laser sintering or direct metal manufacturing, there's lots of different components that can be additive in the aerospace industry. Any questions or comments? Okay, so I guess this is just a reminder to think about not only the high-end applications for additive manufacturing in aerospace. We always point to the titanium parts or the engine components, but the inside of the airplane is also a really important part, especially if you're in commercial aviation or you're doing custom aircraft interiors. And so there's a lot of cool manufacturing that can happen in that business as well. So manufacturers have caught on to this. And so this is just a news item on new plastic composite materials for aerospace 3D printing. And so this is what EOS calls a ALM HP 1130. So you see all these crazy designations, but this is a carbon fiber reinforced polyamide 11. So this is PA 11, which is usually used in SLS additive manufacturing, and it's carbon fiber reinforced. And so this part here was produced using an EOS SLS machine. And so now this material, so this is talking about polyamide 11 in the first paragraph here, and then they talk about this polyamide 12 that's filled with lightweight glass microspheres, providing the same properties as a composite polyamide. So glass-filled polyamide is basically like glass reinforced nylon, but lower weight. And so this is really interesting because this is taking materials that have been used in aerospace and high-end polymer manufacturing for a long time, nylons and filled nylons, and really adapting that to additive manufacturing. And so that's interesting because they mentioned the density. So 0.82 grams per cc is a pretty light polymer, but they're getting nylon strength and it's reinforced as well. And they can make really interesting components because they're using SLS. So this is from 2018. The world has changed in the last couple of years. And so we see a lot of these announcements now where materials companies and additive manufacturing companies are really targeting very specific niches in the medical field, in aerospace, in automotive, in order to meet the performance and cost requirements of whatever sector they're interested in. So if you're interested in all sorts of AM materials, there's a lot of offerings out there, and you can find those. So standards is also important, as Kyle indicated. You know, certification of components is important to the FAA in order to get your products in the marketplace. And there's a lot of certification bodies like the National Institute for Aviation Research and SAE, which are interested in 3D printing standards for the aerospace and other industries. And so this is just one place to look for standards, for quality assurance, for how you do manufacturing with additive manufacturing for these different industries. And these are constantly evolving as additive manufacturing evolves and as additive manufacturing becomes more and more a part of traditional manufacturing operations. And so there's a lot of really interesting concepts out there in terms of additive manufacturing of larger scale components. So we just talked about some of the small scale stuff and about stuff that's possible today, but there's a lot of concepts out there that people are looking at for next generation aircraft wings, or in this case, composite wind blades. So if you've ever seen these huge composite wind blades driving down the road on the back of one of these oversized semi-trailers, they're humongous. And so being able to additively manufacture those is an interesting value proposition where you don't need these huge jigs and fixtures in order to make these components. So you can check this out in terms of this opinion piece on manufacturing composite wind blades. This is starting to come into tooling now in additive manufacturing. And this is a news item from Oak Ridge National Lab. This was printed on a BAM. And this is a person from the Guinness Book of World Records who's measuring this component. And so at the time of this news release, this was the largest additively manufactured component in the world. That's why Guinness Book of World Records is there with their official certification. But now this is a trim tool. So this is a negative of an airplane wing. And this is used to check the dimensions and to cut an aluminum skin that's going to go onto an airplane wing scaffold. So this is a big jig or a big sort of piece of tooling for aerospace manufacturing, but this is really where things are headed in terms of large scale additive. And this is machined and coated, and there's lots of post-processing done to this in order to get the right dimensions and in order to get the surface quality needed. But AM is a unique way to make these larger scale jigs and fixtures. And Oak Ridge has demonstrated that. You can check out the press release, and they also wrote a technical report in this link right here on this trim tool for an airplane wing. This is some of the other large scale stuff that they've done. So this is mold for these big blades. And so these are the wind turbine blades. And so they're usually made in these large molds using some sort of vacuum assisted layup procedure. And so now you can make tools, or you can additively manufacture tooling to facilitate the design and manufacture of these large scale blades. And so this is just a couple of photographs of what they're interested in for large scale additive. Again, not additiving the blade necessarily, but additiving the tools that are used to make the blade. Finally, there's a couple cool things in the space part of aerospace. And so this is a picture from the ISS. And so there's a printer, or at least one printer on the International Space Station, and they printed this little wrench using this printer right here. And there's a company called Made in Space. They have a lot of interesting material extrusion AM technology, and they're working on other types of AM in space as well. This is cool because it has a Lowe's sticker on it. And so they were part of the sponsor for this mission, and they built this multi-tool right here using material extrusion additive. And we talked about particles, we talked about the hazards that are associated with AM. And of course, when you're in the International Space Station, particles are not a great thing to have around. And so they have this printer enclosed in its special environment that's needed to keep all those particles out of the living space of the ISS. But you can check this out online if you're interested in this. And so they talk about eventually printing replacement organs in space. First, they're going to print probably tools, then maybe they'll print components, then maybe they'll print shelters, and eventually we'll get to other sorts of biomedical manufacturing in space. But this is an enabling technology because there's never been an injection molder in space. Maybe there's been some simple CNC machines, but now you can do manufacturing of whatever you want, because as long as you have a printer and some feedstock, all you need is a digital file. And so you can make this wrench or make a different wrench, or you don't have to bring everything up with you, which is pretty interesting. Any questions or comments on this, or things that people want to talk about? All right, I'm going to try and play this next video because it's cool. Let me see if I can stop sharing. Let me go back to my iPad here because I had this video queued up. Oh, this PowerPoint's just never going to be healed. But anyway, this, well, there's the Kronos video if you want to see that. But this video is really cool because they're talking about how they're using 3D printing to manufacture the next generation of space vehicles. And if you've ever seen The Martian, these look a lot like the vehicles that they used in the movie The Martian. And that's where a lot of this inspiration came from. But this is how they talk about how NASA is using additive manufacturing in their design process. So let's check this video out here, if it plays.
We retired the space shuttle this past year after 30 years of excellent service to our nation, and its time had come. It had been a fantastic program. It had done amazing things, but now NASA is ready to really take the next step, which is a more continued presence in outer space beyond low Earth orbit. Our ultimate goal is to get humans to Mars. When we started this project, we thought we were really clever thinkers. We had some technology we wanted to explore that involved multiple wheels and the ability to turn in any direction. They thought, well, what if we build a cabin and have the crew go out for multiple days? That's really where this small pressurized rover concept has really evolved into the space exploration vehicle.
So the SEV will hold 2 astronauts. They basically live in this module, in this rover. It's your own personal SUV in space. You always want it to be as light as possible. You also want it to be strong enough that it's got your safety factors, that nobody's going to get hurt. You're going at several thousand miles per hour just to escape the Earth's atmosphere. So you've got to be able to handle all these vibrations and all these different things just to be able to get out into space. And the vehicle can't be damaged. There's probably around 60 to 80 parts on this particular rover. It's all done by additive manufacturing for a lot of different reasons. You know, sometimes traditional manufacturing methods don't really work for some parts that you want to build, where you can do it with additive manufacturing, and it's really simple. It really takes no effort for what would otherwise be a very complex process. Whether it be ducting that's got flame retardant characteristics and properties to it to help keep people safe, or different fixtures and different parts. There's absolutely a place for additive manufacturing. There's a lot of things that you don't see that really get to go on is the design verification and the functionality checks of parts before we send them to be manufactured. If the final product is not going to be an additive manufacturing plastic part, we will do it in a rapid prototype fashion where you'll get it back in maybe an hour, a day. What that allows us to do is be able to check our design and make sure that everything's going to work the way we think it is. Sometimes vendor components are a little bit different than what you anticipated, what the drawings say. So you're able to functionally build up this assembly and check it to say, hey, this is what we want, or hey, we need to make some tweaks. So by doing additive manufacturing, rapid prototyping, it allows you to keep your costs down. Everybody's got a budget to deal with, and we're no different. Being able to make a difference and leave my mark is really what inspires me. You know, that's what gives me the drive to do what I do.
Okay, so that's really interesting. Let me share my screen again to get back to the PowerPoint slides. And what's interesting that they talked about in aerospace development, actually using additive manufacturing, which we think about as expensive, as a cost savings for aerospace component development. And they're using just FDM. And of course, this is probably a coated part because it's nice and smooth. It's white in the video. They just highlighted it in yellow here. But using FDM to produce these custom covers or custom electronics holders, that's a really interesting part of how to mock up unique vehicles or how to mock up interiors and make tweaks. So you don't need the highest tech additive to do stuff like this. They're using Stratasys FDM machines to mock up the next Mars rover. So that's pretty cool. All right. Any questions or comments on that? So when we think about composites, so we've talked a lot about polymers and Ultem and we can identify and polyamide 11 and 12. We can identify a lot of the polymers that are used in these types of industries. But when we start to think about additive manufacturing of composites, there's lots of different types of tweaks that we need to consider. And so the additive manufacturing industry is detailed in this article here. When you go to composite additive manufacturing and think about the composite part, you've got continuous fiber, you've got long or short fiber or chopped fiber composites, you have nanocomposites or particles, and we've talked a little bit about each of these, but you can see that the processing and the different types of processing tweaks and different additive processes, whether you're interested in SLA or SLS or FDM, they each have a distinct role to play depending on what the composite materials are, what the polymer is, and what the composite filler is. And so it's interesting to think about where you're, if you're interested in a certain material or interested in a certain process, where that might fit into this map, or if you're interested in, or how your process is related to other processes that are out there. So you can just take a look at this, but we've talked a lot about multi-jet fusion, we've talked about FDM, we've talked about SLA, and this chart sort of wraps all that together and how these processes might relate to each other. One of the things that people are doing a lot with now is doing structural assemblies with composites. So we've talked about mobility or we've talked about smaller components, but there's a lot of infrastructure development out there with additives. So people are interested in concrete 3D printing, but it turns out that making these composite bridges or these walkways or making structures out of polymers and composites is something that folks are interested in for urban renewal. Of course, polymer bridges don't rust, they don't have to be painted, they don't crumble like concrete. So there's some really cool articles out there in terms of using polymers and composites for infrastructure or architectural purposes. And so this is one demonstration of a pedestrian bridge, and here is another demonstration right here. So using additive manufacturing, some places have printed these sort of structures in place. So they bring the additive manufacturing technology right to where they're going to put the bridge, or you can print the bridge in a warehouse, and since it's plastic and light, you can easily move it to where it's going to be used. And so they don't necessarily describe this bridge at Tanji University as to exactly what the materials were, but they say it's a modified plastic, and you can see that you can get some really interesting architectural features out of the types of 3D printing that we've talked about. So not only aerospace, automotive, biomedical, but now we can include some of this custom architecture as well. And there's some really interesting news articles out there for using additive manufacturing for bridges, especially. And so when we think about these different types of composites, again, just thinking about what the technology is, what the filler is, what the polymer is, and there's a lot of articles out there. This is one reference right here in the literature that's a collection of other references, basically pointing to maximum tensile strength improvements compared to pure polymer, exactly what the system is, and then lining up whether it's a short glass fiber ABS or whether it's continuous carbon fiber PLA. How do you do that additive manufacturing of whatever composite material you're interested in? So there's a lot of these out there, depending on, again, whether you're interested in solvent cast direct writing or DLP, etc. There's a lot of unique composite properties and unique composite materials out there in the literature. And so here's one for biomedical applications. You can take a look at that. And so the one area that people are doing a lot of innovation in, and that's why I pointed to this review article right here, is that some types of composites are still difficult to additively manufacture. So even though there's a lot of examples out there, you sort of see the same stuff in whether it's material extrusion AM or FDM, or whether it's SLS or SLA. You know, those processes lend themselves to certain form factors, but people are innovating in terms of how do you integrate the types of composites that have the highest strength and highest performance into this idea of additive. So this is one cool example right here, and here's the literature reference at the bottom. You can get the direct link and look at how they're using continuous carbon fibers. And in this case, this is material extrusion AM of PLA. So we already know about the material extrusion AM with the heated liquefier and the plastic filament, but now this is putting a continuous carbon fiber inside the road. And this is a type of material extrusion AM that we haven't talked about in class, is how do you get continuous carbon fiber? We've seen a couple little videos of this, but if you look at how sporting goods are manufactured, or if you look at how aircraft carbon fiber composites are manufactured right now, it's usually continuous fiber. And so continuous fibers are the strongest fibers out there. They yield the strongest components. There's certain methodologies for when you make a continuous fiber composite versus when you might make a woven carbon fiber mat composite. But being able to use continuous fibers versus chopped carbon fiber or nanocomposites or something like that is important. And so now this article describes how you might integrate continuous fibers with material extrusion AM. And you really want to produce parts that now look like this. So here is our heated liquefier. This looks like your garden variety MakerBot. And now you have carbon fiber reinforced PLA that's reinforced along the road direction. So of course, if you're just making a flat sheet, that's not very interesting. The carbon fiber is just looped back and forth, as shown in this diagram in the bottom right here. But you could make something that looks like an aeroform or a cross-section of an airplane wing right here, or a cylinder where this could be a pressure vessel or a fuselage or something like that. And so this carbon fiber, this continuous carbon fiber composite now looks like carbon fibers that are embedded in a PLA matrix, not a line chop fiber like we would get in BAM or some of the other examples that we've looked at, but in terms of continuous carbon fibers embedded in a resin matrix. And this looks a lot like the types of composites that are used in thermoplastic carbon fiber composites for these high-end applications. So we'll pick this up next time, because this is now the intersection of all the stuff we've learned about composites, sizing agents, matrices, fillers, some new types of additive technology, and these high-end applications where you can't get the properties from chopped fiber composites that you can from these continuous fiber composites. And we'll talk a little bit about this because this has relevance for aerospace and automotive and high-strength applications of polymer and composite AM. Any final questions here before we sign off for today? Okay, well, I will be available for office hours by Zoom. I encourage you to keep plugging away on your projects and presentations and get those in when you can. And I'll see you on Zoom on Thursday. Thank you very much.
Thank you.